So today's lesson, we're going to learn how to take our knowledge about Lewis structures and what they look like in 2 dimensions, and now we're going to put them into 3 dimensions. So this theory is going to help us figure out how to draw molecules in 3D, which also leads to discussions about their properties, the way they behave, and so on. So this theory is called Vesper theory. It's an acronym for valence shell electron pair repulsion theory. It sounds like a big mouthful and kind of confusing, but let's take a look at the name even before we start, and hopefully you'll see that it doesn't sound so scary. So first thing, and first part of the name is the valence shell component. So valence we know is the outermost orbital. So we're looking at the outermost orbital and energy level here. Then we're looking at electron pair. So we're looking at pairs of electrons in that outermost orbital. And then we've got the word repulsion. So we know 2 electrons together as pairs doesn't make a lot of sense when we write it on paper because they're 2 negatively charged particles. So those 2 electrons, while they are paired up in the same orbital, they're going to repel each other as much as possible. So this theory takes the electrons and how they repel each other in those valence orbitals and helps describe their molecules in 3D. So what are some main key components of Vesper theory? When we look at molecules, they want to be as stable as possible. So whatever shape that they take on is going to be the lowest in energy, the most stable. What this means in terms of the electrons, any energy that's any shape that's low in energy is one that's going to try and minimize that repulsion. So those electrons that are in those valence orbitals, we want their energy to be minimized as much as possible. So that means they're going to be spread out as far as possible, and we'll see how that works in a few minutes. There's 2 ways you can see electrons paired up and how they repel one another. We know electrons can be found in 2 spots in our diagrams. When we drew our Lewis diagrams, there's chemical bonds. We call those bond pairs, or you'll see the notation BP for short. So when electrons are actually in a bond between 2 atoms. Or you can see electrons when they're unshared in lone pairs. Lone pairs were those dots or electrons that we put in our Lewis diagrams. That's why we still wanted to include them in our diagrams, because it helps determine 3-dimensional shape. You'll see that notation written as LP or lone pairs. Another way of thinking about Vesper theory, if you want one that's a little bit more simplistic, it leaves out a little bit of information, but think about your knowledge on electrostatic charges. When you have 2 items like electrons that are both negatively charged, they're going to repel one another. So the closer you try and bring those 2 negative charges, the more they're going to push back and try and repel one another. If you think about taking 2 ends of a magnet that have the same charge on them and bring them together, you can feel that force pushing the 2 ends of that magnet apart. It's exactly the same idea here with the electrons. So whether they're in bonds or whether they're in lone pairs, in molecules, the electrons will try and spread out as far as possible to minimize that repulsion. It depends on how many atoms are there and the types of bonds or lone pairs that are involved, but they will spread out in 3D as much as possible to try and stabilize their configuration and minimize that repulsion that's there. So to give you an idea of where we're going, take a look at this example with methane, which is CH4. If you were to make a quick Lewis sketch of CH4 based on what you've learned, you might make a diagram that looks something like this. Now that's flat, 2-dimensional, and it's not accurate for its real shape. If you draw it like that, which is what's represented here with the ball and stick model, the angles between the bonds are 90 degrees if we were to draw it in 2 dimensions like this. If we start thinking in 3 dimensions, adding that 3rd dimension adds more space for those electrons to spread out, which means we can minimize the repulsion more. So by introducing the third dimension, which is shown here, if you look at the ball and stick model of methane, you can see that they're spread out differently. And now if we measure that bond angle between these two here, the bond angle is now a lot greater. So we've got a 90-degree angle here versus an angle of 109.5 degrees over here. Obviously, the one that's in 3D has a larger bond angle, 109.5. That means that the electrons are spread out more, and this configuration over here minimizes that repulsion between the electrons. So this is the actual configuration or three-dimensional model that methane will adopt. So when we learn about Vesper in today's lesson, you're going to learn how we go from our two-dimensional Lewis diagrams and try and change them into three-dimensional shapes based on this exact idea, minimizing repulsion between electrons. So how do we do it? There's a lot of different terms and measurements and names here, but we'll break them down one at a time, and hopefully as we go through them, you'll get to see how this all works. In Vesper theory, there's 5 basic groups. We call them electron geometry groups. Think of them like 5 main groups or 5 main families. And based on different options within these groups, you can have a variety of different electron arrangements that can be made, and therefore you'll get a whole bunch of different shapes that will be generated for the molecules that you're looking at. So the first 5 groups are linear, trigonal planar, tetrahedral, trigonal bi-pyramidal, and octahedral. We're going to walk through each of these groups, and as we go through them, you'll see that there's a variety of different shapes that can be generated. When we talk about electron geometry groups, we refer to a few more terms. If you hear the term electron group, it means we can refer to a single bond, a double bond, a triple bond. They're all treated equally, even though there's multiple bonds there. They're all each considered one electron group. Those are our bonded pairs. Or electron groups are also considered those unpaired electrons, your lone pair electron groups that are there. Now in the notes that are posted, there's a nice chart. It's a PDF, 2 pages. If you're going to consider anything for studying and reviewing, this chart is probably the best one to have. Even if you can print this one off and keep it handy, this one would be the one I would recommend. It looks like this. So it takes you through the electron groups and the geometry names, and then it goes through what happens when you change the types of pairs involved, what's the actual molecular shape, and then an example that goes along with each of them. So it might not be a bad idea to even have it out now so you can follow along, but definitely after you're done the lesson, this is one that you'll want to keep handy if you want everything kind of condensed in one simple file. So we're going to start off with our 2 electron group. This electron geometry group is the linear family. In the linear family, there's only one shape that's possibly generated. It's a linear shape, and the linear shape can only have 2 bonded pairs. Remember, bonded pairs could be a single bond, double bond, or triple bond. When we refer to 2 bonded pairs, or when we're talking about bonded pairs, we're always trying to refer, well, what's going on around the central atom. So this is what a linear shape looks like. The red atom here is our central atom, and we have 2 bonded pairs on the outside. This here is 1 bonded pair, and this here is 1 bonded pair. So 1 bonded pair plus 1 bonded pair gives us the two bonded pairs over here. So in this group, in the linear group, we can only have one actual shape, one molecular shape, and that shape is called linear. This one's the most simple of all the groups. Now on this, you'll also see the bond angles are listed. So we'll walk through how to draw these and represent them, and we'll add on the bond angles next. So our electron geometry group here for practice, this group is called linear, and its actual molecular shape is also called linear. Since we don't have molecular model kits at home, I've included a ball and stick model over here for us to take a quick look at, and then we're going to try and draw it ourselves. So here's our central atom, 1, 2, there's two bonded pairs here. Two bonded pairs means we're in the 2 electron group family, which is why we're up here saying we've got linear family. When we only have 2 bonded pairs, it takes on a molecular shape. The bond angle is always between bonds. So since this is linear, the only way to measure bond angle would be from one side to the other, and that one's 180 degrees. So if I were trying to draw a molecule that takes on a linear shape and draw it with proper geometry, it's not a hard one. This one's the easiest one to draw. You can either draw the actual atoms or just draw the ball and stick model, which is a lot easier. When you draw them, you want to try and draw them to the best of your ability by hand. So if it's going to be linear, draw it in a line, and you want to make sure it looks like it's 180 degrees. And you can label on that bond angle there. Let's go on to the next group. The next group is one where you can have 3 electron groups. So this can be a combination of bonded pairs or bonded pairs and lone pairs. This group, the electron geometry group, is called trigonal planar. If we think about that name for a minute, we know the prefix tri means 3. So there's 3 to this. And if you see the word planar, it means it's a 2-dimensional shape. Everything lies in one plane. So this is a plane that has 3 groups lying in one plane. The shape of this group arrangement, if anyone has a fidget spinner at home, grab it, take a look at it. But if you know what it is, there's a central part to the fidget spinner where you can hold on, and there's 3 prongs on the outside that you can spin, but it's all flat. That's a very good comparison to what this shape would actually look like. So, what happens if you find yourself with a molecule with 3 electron groups? If you look at the molecule and all 3 electron groups are bonds, bonded pairs, the actual shape is also called trigonal planar. If you have all bonded pairs, 3 of them, they'll always match the family or group name they belong to. But if we say we had something different, what if there's 2 bonded pairs and 1 lone pair? The actual shape name changes. It's often called bent or V-shape, or another one that you might see is angular. That's another one. Any one of those are acceptable ways to describe the actual shape. Over here, you'll see the options. This is with 3 bonded pairs, 1, 2, 3, 3 bonds to other atoms. Where over here, you have 2 bonds to other atoms, and then this is the lone pair here. They're showing the electron cloud where the electrons are found, but you don't need to necessarily draw that in. But it's part of the reason why the shape stays the way that it is. Those electrons are there, and it forces those bonds to stay further away. Remember, they're all electron pairs here, so we're trying to minimize or spread out the electron arrangement that's there. Now we're going to take a look at the angles. So listed down here are your two angles. When we look at trigonal planar, you've got 360 degrees around in a circle. 360 divided by 3, that's where you're going to get your 120. Over here, when you introduce a lone pair, you'll notice that the bond angle changes slightly. It says less than 120, but we're just going to pretend or assume that it's approximately 120 because the exact bond angles can vary depending on the atoms that are there. So we'll just approximate the bond angle to the same 120. Okay, so when we look at our diagram here, our electron geometry group, it's going to be 3. So that's going to be trigonal planar. And over here we have 3 bonded pairs. Here's our central atom, 1, 2, 3. When we have 3 bonded pairs, the actual molecular shape name is going to be trigonal planar. When we draw out trigonal planar, we want to draw out those 3 bonds and space them out approximately evenly when we draw them like that. And our bond angle here is going to be 120 degrees between them. Here we have 3 electron groups, 2 bonded pairs, and 1 lone pair. When we have 2 bonded pairs and 1 lone pair, we said that this shape is going to be bent, or you could call it V-shape, or you could call it angular. It doesn't matter. When we draw it out, again, try and maintain that bond angle. Think about here, we've got all these 3 spread out 120 degrees. We're keeping the bottom 2 bonds and replacing the top bond here with a lone pair. So the bond angle in here, even though it says less than 120 to be truthful, we're just going to say it's about 120. Now we're going to move on to some groups that will have some 3 dimensions to them as we move through. So what happens now if we have 4 different electron groups around the central atom? This is where we get into something called tetrahedral group or tetrahedral electron geometry. Our first option here, 1, 2, 3, 4 bonds. When we have 4 bonds around the central atom, the actual shape is still called tetrahedral. Always when all of the pairs are bonded pairs, the name of the group and the actual shape are always the same. Next, we've got 3 bonded pairs and 1 lone pair. So imagine we take our tetrahedral shape, we eliminate one of the bonds and replace it with a lone pair. The shape that we see is only based on the bonds. This one's called trigonal pyramidal. And then imagine if we take away yet one more of those bonds, 2 bonded pairs and 2 lone pairs. So in this diagram, we've taken away this bond here and replaced it with a lone pair. If that happens, we get another bent shape or V shape. Now the bond angles here though are different. Tetrahedral bond angles, because we've got them in 3D, are 109.5 degrees. Again, when we replace any of the bonds with lone pairs, the bond angle does decrease, but by what exact amount it can vary, so we'll just approximate it at 109.5. So let's take a look at some of these shapes together. So again, electron geometry group here for practice. This one is tetrahedral. All of these have 4 electron groups around the center. Our first one has 1, 2, 3, 4 bonded pairs. When they're 4 bonded pairs, this molecular shape that we see is tetrahedral. When we draw out tetrahedral, you can see in the ball and stick model we're now into 3D. Obviously, for you trying to draw this in 3D on paper isn't going to be possible. Definitely not for me. I'm not artistic. So how do we get around this? You may have seen this back in grade 11. So for this one, we've got a couple of bonds that are in the same plane. So the one pointing straight up to the one in the center, and one of them on the side. When you draw it, you can keep these ones all on the same plane and represent them with a regular line. But then we've got these other bonds here. One's kind of pointing back and one's pointing forward. To show the ones that are pointing back, we do a dashed line to show it's pointing backwards. And then one's coming forward, we use a wedged line that gets bigger pointing out. We want to try and spread these out the best we can to represent our bond angle. All of the bond angles for all of these ones are 109.5. So when you draw it, don't draw it straight across so it looks like it's at 90 degrees. Put it on an angle so it represents the actual bonding angle that's there. Next, we go to this shape. This shape has 3 bonded pairs, and then it has 1 pair of electrons here, so 1 lone pair. Still 4 groups total. 3 plus 1 still gives us 4 groups, which is why it's in tetrahedral group. This shape is called Trigonal pyramidal. If you're trying to visualize what this shape looks like, think of a tripod. Everyone's familiar with a tripod. This shape, trigonal pyramidal, more common name, tripod shape. We're not going to call it tripod here, but just for your reference, you can refer to it as tripod. So when we draw it, we want to draw it so it looks like a tripod. If we go back to our diagram over here with tetrahedral, what we're going to do is draw this same diagram, but instead of this one group that's pointing straight up at the top, we're going to replace it with a lone pair. So here's our central atom. Put in our lone pair. One bond to the side, one bond going back, and one bond pointing straight out. And then here again, bond angle is approximately 109.5. Last one, we've got 2 bonded pairs and 2 lone pairs. 2 plus 2 gives us 4. So we're still in tetrahedral. This shape is your bent shape. Now you might be thinking, hey, we just saw a bent shape back with trigonal planar. True, this is another bent shape. When you draw it, it will look very similar. You'll have an extra lone pair here. But one thing to watch out for, the angle's different. Because there's 4 electron groups around the center, the electrons have a little bit less space to spread out. So here the bond angle is about 109.5. When we looked at the bent shape in the trigonal planar family, it only had 3 groups to spread out, and its bond angle was about 120. So just remember there are 2 bent shapes, but depending on which group it falls in, the bond angle will vary. The next group has the most particular shapes. This one's called Trigonal bi-pyramidal group, 5 electron groups, and there's quite a variety of different shapes here. When all 5 are bonded pairs, like the first diagram here, it's called a trigonal bi-pyramidal shape as well. Next, what happens if we take away one of the bonded pairs and replace it with a lone pair? So we've taken this bond away and replaced it with a lone pair here. The molecular shape changes, it looks different, and it's called a seesaw shape. And we'll go over why it's called seesaw in a minute. Next, what if we take away yet another one of these bonds? So take away yet another one around the middle. So we have 2 lone pairs and 3 bonded pairs. The shape changes to a T shape. Then if we take away yet one more bonded pair, there's 3 lone pairs around the center, and then 2 bonded pairs. We get a linear shape. So let's go over the shapes that are here and the angles, because there's a lot going on. And then you can flip back and look at that chart to see how everything's summarized. So this electron group is called Trigonal bi-pyramidal. So there are 4 different shapes you can get. This one is when you have 5 bonded pairs. 5 bonded pairs, the molecular shape is trigonal bi-pyramidal. Now, for this one, when we look at it, there's a couple of places for angles. So first, you've got axial positions and you've got equatorial positions. So when we're thinking about this molecule, think about this one as North Pole, South Pole, and then you have 3 bonds evenly spread out around the equator, axial and equatorial positions. Between the North Pole or South Pole and anyone around the equator, it's 90 degrees. Then you've got bond angles between the ones that are on the equator. If we think about a circle around the equator, circle means 360 degrees. We have 3 bonds around that 360 degrees. Here is 120. Think about that trigonal planar shape. Around the equator, those atoms are arranged in that trigonal planar arrangement. Then you could also add in an extra bond angle between the North and South Pole. That's not as common, but if you wanted to, this one is 180 degrees. So lots of bond angles going on. How do we draw this one? Take your central atom, North Pole, South Pole. One of the ones around the equator will also be in the same plane. So you can draw it straight like that. And then you've got 2 on angles. One pointing backwards and one pointing forwards like that. Now, let's look at what happens when we start replacing bonded pairs with lone pairs. Around the equator, since the bond angles around the equator in that plane are 120 versus the North and South Pole are 180, the 180 is a larger bond angle. So if we're trying to minimize repulsion, we're going to take away ones from the equator. So here, imagine we take one of the bonds away from around the equator. Let's say we take away this one here. And we've just rotated that molecule so it looks like this. This one is called a seesaw shape. Why do we call it seesaw? Because it kind of looks like a seesaw. These are the 2 mid parts of the seesaw. This would be one seat on the seesaw, and this would be on the other. And it would actually seesaw back and forth if we were able to build this out of the molecule kit, so you can teeter-totter it back and forth. Bond angles for this one, same thing. The North and South Pole, even though they've been flipped on their side, are still 180. These guys on the equator are about 120. And then it's a little bit awkward with this angle, but in here you have that right angle of 90 degrees. So how do we draw this one? We're going to take this molecule and flip it on its side and just eliminate that bond that's there. So central atom, North Pole, South Pole, one bond coming out, one bond coming behind. And if you want to put in that lone pair, you can put that in. It's always helpful to draw your actual molecular shapes the same way that their names are representing, because that way it helps you try and visualize what's going on. All right, let's keep going. Next, we've got 2 lone pairs, and we've got 3 bonded pairs. When that happens, you get a T-shaped molecule. So with this one, we have our north and south pole, and we've taken away 2 bonds from the equator. So we're left with 1 on the equator, 1 north pole, 1 south pole here. Bond angles for all of these are 90, and between these two is still 180. This one's nice and easy to draw. It's a 2-dimensional shape. It's all planar. So this one, when you draw it, literally just draw it like a T shape, north and south pole, 1 on the equator. And again, if you like to keep those electrons in there to show that they're forcing that shape that way, then that's a good way of thinking of it. Last one over here, what happens when we have 2 bonded pairs and 3 lone pairs? All of the lone pairs take the positions of the bonds that were on the equator. So all of those are still taking the equator position. They're still spread out 120 degrees from one another. And now we just have our north and our south pole left, and we know that's 180. This one, again, very easy to draw. It's our linear shape. So when we draw it, we're just going to draw it like a line, right in a line, 180. And again, if you want to put those on just for reference, they're there. Last group that we're going to look at, what happens when you have 6 electron groups? 6 electron groups where the electron geometry is called octahedral. Octahedral comes from the actual shape that would form with this molecule. 4-sided pyramid on the top, 1, 2, 3, 4, and 4-sided pyramid on the bottom, 1, 2, 3, 4. Think octahedron shape if you go back to your math and what you've learned a long time ago with geometry. First scenario, what happens if they're all bonded pairs, all bonds? The actual shape is still called octahedral. That hasn't changed. But now what happens? What if we start looking at lone pairs? We replace any one of the bonds with a lone pair. The shape changes to one called square pyramidal. 5 bonded pairs, 1 lone pair. What happens if we take away another set of electrons in a bond? So now we have 4 bonded pairs and 2 lone pairs. The shape of this one's called square planar. Here with all of the 6 groups, they're all arranged equally around the central atom, so the bond angles are approximately 90 degrees. So let's do the same thing, and then we're going to try and put it together with our Lewis diagrams. So electron geometry group is octahedral. This one we have 6 bonded pairs, and its actual molecular shape is octahedral as well. All of the bond angles here are 90 degrees, so let's work out how that happens. Remember our analogy with north and south pole, keep that in mind. North pole, south pole, all in one line. We have 4 positions around the equator. Around the equator we know is 360. 360 divided by 4 gives us 90. So in here we've got 90-degree angles. In here we've got 90-degree angles between the poles in the equator. And then of course you've got your north and south pole at 180 degrees. To draw this one, not too difficult. North pole, south pole, and then we're going to do 2 pointing away from us in the back and 2 pointing forwards. Now what happens if we remove one of the bonded pairs with a lone pair? Since everything here is all 90 degrees between the two planes, we can remove any one of the pairs. So we're taking away one from the bottom here and replacing it with a lone pair. Again, still everything here is about 90 degrees to one another. When we do that, this is called square pyramidal. Why is this one called square pyramidal? It looks like a square-based pyramid. Here's the square around the bottom. Imagine drawing those together and you would get a square. And then there's the top of the pyramid there. When drawing this one, we're going to use this as our reference point. It's going to be exactly the same, except the bond at the bottom is not going to be there. So central atom, one to the top, back, back, one forward, and our lone pair would be hiding in there. This one again, 5 bonded pairs, 1 lone pair. Lastly, we've got our 4 bonded pairs and 2 lone pairs. So with this one, we've taken away the north and the south pole. Taken away north, taken away south. So what we're left with is 4 around the equator. 4 around the equator, remember, are all 90 degrees to one another. This shape is called square planar. Again, remember you see that word planar, we think 2D. So essentially with this one, it's really easy. If we took our 4 atoms and arranged them around, it would essentially look like a plus or a cross. And then we've got our 2 lone pairs that sit in that plane there. So now we've walked through all the different shapes. This is the summary chart that's in your textbook if you like that one, or you can refer to the one that I showed you at the beginning of the lesson. But now we'll try a few examples of how to take Vesper and Lewis diagrams and put them together. So we're just going to do a few of these together, and hopefully you'll be able to see how it works. So let's try CCl4 first. So first thing I'm going to do is draw my 2-dimensional Lewis diagram, just like we learned in the previous lesson. There are 32 valence electrons in my diagram for CCl4, carbon tetrachloride. Carbon goes in the center. Chlorines are going to be joined around the carbon. And I make sure I account for all my electrons. If you're still having a hard time with Lewis diagrams, you've definitely got to have them down packed, lots of practice, really comfortable with them, because you need to know how to draw a perfect Lewis diagram to go on to Vesper and put it in 3D. So this is your Lewis diagram. Now we're going to change it into 3-dimensional structure. So we look at carbon. How many groups are bonded around carbon? 1, 2, 3, 4. And they're all bonds. So this means there are 4 bonded pairs around the central atom. If we go back to our chart, 4 bonded pairs means our electron group geometry, or our family, is tetrahedral. So it belongs to the tetrahedral family. Since we only have 4 bonded pairs, our molecular shape, when we have 4 bonded pairs, is also tetrahedral. So now we know the actual shape and the group it belongs to. So now we're going to redraw this in 3 dimensions. So it has to have a tetrahedral shape. You can draw it with the actual atoms, or you can use a ball and stick model. It doesn't matter. Here's our central atom. For tetrahedral shape, one goes to the top, one goes to the side, one going backwards, one going forwards. And I want you to also practice putting in the bond angles, because that'll give you a good idea of the spatial arrangement. all of the bond angles for this one are 109.5 degrees. So we took our Lewis diagram, counted the electron groups around the central atom, figured out there's 4 bonded pairs, and we took that back to our chart. 4 electron groups and 4 bonded pairs means we have a tetrahedral electron group family, and 4 bonded pairs only means the same shape name, tetrahedral, and we're able to draw that. Let's try another one. What if we have SF4? If we count the valence electrons for this one, you would get 34 electrons. So I do my Lewis diagram sketch, spread out my fluorines, put in my electrons, filling up the ones on the outside first. When I count, I've got 32 electrons. The last 2 have to go on the center. Now when I look at the geometry here, I have to count. 1, 2, 3, 4, 5. There are 5 electron groups around the central atom. 4 bonded pairs and 1 lone pair. So this means I have 5 electron groups. So my electron geometry with 5 groups is trigonal bi-pyramidal. If I'm in the trigonal bi-pyramidal family, I have to look, what's the actual shape when I have 4 bonded pairs and 1 lone pair? So when I go back to my chart, 4 bonded pairs and 1 lone pair means I have my seesaw shape. So this molecule, SF4, when I draw it in 3D, should take on a seesaw shape. If you're going to use ball and stick model, that's nice and easy. I've got 2 here. I've got my lone pair, and then I've got 1 pointing out at me, and kind of 1 pointing back. And again, remember with this one, bond angles here around the equator are 120, and our north and south pole are 180. If you want to draw these in with the atoms, you can. If you did that, it would just look like this. So instead of just the circles, you put in your actual atoms there. So that's definitely something you could do as well. Now, if you want to try a couple on your own, there's 2 that you could try. Let's flip back here. We did this one together and this one. If you want to pause the video and try out IF5 and XEF4, these 2 here, give that a shot now that you see what we're doing. And when you're ready, you can unpause and I'll walk through those last 2 together to finish off the lesson. All right, IF5. If you're ready to check, here we go. IF5, if we count up the valence electrons, there should be 42 of them. So, iodine in the center, put my fluorines around, and then I'm going to put my electrons on. So when I check 8, 8, 8, 8, 8, 8 times 5 is 40. I've got 2 more. They've got to go on the center for 42. Now I count my electron groups. 1, 2, 3, 4, 5, 6. I have 6 electron groups around my central atom. 1, 2, 3, 4, 5. 5 bonded pairs and 1 lone pair. So my electron group geometry or family, when I have 6 groups, 5 plus 1 is 6, means it belongs to the octahedral family. And my actual shape, I have to go and check. Actual shape, 5 bonded pairs and 1 lone pair, should be square pyramidal. So now that I know it's square pyramidal, I can start to draw my molecule. Ball or stick or with the atoms doesn't matter. Here's my central atom. When I do square pyramidal, I keep my north pole, and my south pole is going to be replaced by a lone pair. Then I'm going to have 4 groups around the equator. 2 are pointing backwards, and 2 are pointing forwards. And if I want to put in my bond angles, between the North Pole and the equator is 90 degrees, and then also around my equator here is also 90 degrees. Everything with this one are 90-degree bond angles. Okay, last one. Again, if you haven't tried this one, I would recommend just pausing and trying it yourself, but here's the answer. When we count up the valence electrons here, we should have 36 of them total. Xenon goes in the center. I'm going to spread my fluorines around for my 2-dimensional Lewis structure and start putting my electrons around them. I've got 8 times 4 is 32, so I need to put 4 more on the center. 34, 36. Now I count my groups. I have 1, 2, 3, 4, 4 bonded pairs, and I have 1, 2, 2 lone pairs. 4 plus 2 means 6. I have 6 electron groups around the center, so my electron group family that it belongs to is octahedral. But my actual shape here is not the same as my last one, even though it still belonged to octahedral. Because I have 4 bonded pairs and 2 lone pairs, my shape is going to be different. So when I go and look, 4 bonded pairs and 2 lone pairs, it's square pyramidal. So when I draw a square pyramidal, I get rid of my north and south pole, and I only have to show the 4 around the equator. Remember, they're all in one plane for this shape, so I can just draw it so it looks like a plus. Make it nice and easy. And then I've got my 2 other pairs of electrons there. And if I'm putting in my bond angle, everything here is 90 degrees. So, big lesson, lots to learn. Make sure you practice a lot. There's a big worksheet package, 4 sheets you can go through. There's extra additional practice. Plus there's an online simulation and a couple of websites that are worth visiting where you can drag and move the molecular shapes around. I would highly recommend doing that. You may need to download a piece of software involving Java, so I've put the link on the instructions there if you need to and are able to do that. But I would strongly recommend checking those shapes out in 3D online to help reinforce that visual for all of them. So lots of practice, practice away, ask questions. I'll be happy to help.